Right, so let's all get settled because we're about to start. And okay, so today's class begins the revision of the sort of basic mathematical concepts that I think everyone has to have in order to be able to do machine learning. So today we'll talk about probability, and in particular we'll be talking about two very important operations of probability, conditioning and marginalization. I will define these and we'll try a few examples. And these are extremely, extremely important. All of the heavy machine learning algorithms for natural language processing, for translation, for ranking web pages, for doing speech recognition, they all rely on these two very basic operations, marginalization and conditioning. Okay, so they're very important. Before we talk about marginalization and conditioning, let's start from scratch. And let's begin by understanding what probability is. We use the term all the time, but it's good to know what it is and what it is not. Let's start by asking you a question. If I toss a coin, what's the probability that it will be heads? Anyone? Half. Most of you seem to like a half, 50%. Is it a fair coin? Okay. Why would you expect it to be a... Okay, so the next question then is, why would you expect it to be a half?
Based on flipping coins in like before and
okay, so you flip the coin many times, and if you start doing it, assuming that it's an unbiased coin, that I haven't put lead on one side, you probably get tails half of the time. There were some hands up.
I pretty much was thinking the same thing. Other than that, there's only two possibilities, and so you're going to get one of the two. And if it's unbiased, then it's going to be half. Well, approximately half, because there's like that tiny little chance it'll be on end.
Mm-hmm. But some of you, you're also thinking not just frequency, but you're thinking about this question of being biased. And that takes us, so let's write there frequency. Now, that takes us to another question. What's the probability that the Lionsgate Bridge will collapse before the end of the term?
I don't have that information.
Pardon?
I don't know, it hasn't happened before, so
It hasn't happened before, so we just can't deal with this. Does not compute.
look at other bridges and how their history and...
Now, for real, guys, what's the chances that that bridge will collapse before the end of this term? Well, let's start with you.
Small. 0.005%.
0.005. Let's start recording these probabilities. Let's write con compute. 0.005. 0. If I thought like you guys, I probably would never drive over that bridge. I'm more on the 0 side.
I don't think it functions too. I think it's probably expression. You take all the bridges that have been built so far, and you look at how many have fallen, you look at the time that they fall, and you look at the last big bridge, and you say it was built this day,
So what's being pointed out here is you would take all the bridges that have been built and we check how the time of duration until they fell. But now the question to you is, were all those bridges the same? Has there ever been a bridge that looks exactly like the Lions Gate built before?
It depends, because you can't really, no bridge is going to be exactly like landscape. There's no bridge that was at the landscape location before. So
Exactly.
you can take a set of conditions that apply, or let's say a least square sort of situation where you can't get an exact answer, so you approximate. And you apply those conditions to the landscape, and you say, this is a chance that this might apply, this situation might apply to this bridge.
Okay, so let's say, what would those conditions be?
See, probably the same surroundings. So on the Pacific Rim, so there's a probability of the plate or whatever, and the materials that it was built, the load that it's under, and the weather, the corrosion level, the salinity of the sea.
Exactly. So we're starting to hear about what you often call domain knowledge, knowledge about the problem. We're talking about the materials of the bridge, we're talking about the geographical place of the bridge, and so on. So to talk about probability, we don't just rely on frequency. You're relying on something else. You're relying on domain knowledge. And more often, you're not just relying on domain knowledge, but we also learned something from this exercise, that probability is a subjective thing. Every person here, well, not everyone, but people had different views of what was the probability of a bridge collapsing. There was a question here.
I was going to mention that well, the landscape bridge collapsing or it doesn't or not collapsing isn't a well, it's a discrete value. It's either up or it's down, and it can collapse on any given. Like a bunch of things can make it collapse. Like a big tsunami can make it collapse. Like a pin missing, and it's like, to figure out the probability of the entire landscape bridge collapsing, you have to sum over all of those possible possibilities. So I'd say it's impossible to get frequency of landscape bridge collapsing. Either it does or it doesn't, depending on your knowledge of.
It might not be, it might be impossible, but you said 0.005.
That's my own guess.
That's a subjective view, and that guess was an informed guess. It wasn't a crazy guess. It wouldn't have been 0.05.
So there's been three bridges that span that body of water. The Lions Gate, the original second narrows, and the second narrows. And one of those three bridges fell down, so it must be 1 and 3.
We start learning interesting stuff. All right. So this frequentist view of probability is getting us a bit into trouble. Okay? It's the one that we learn in school. Toss a coin many times. But when you start asking questions involving the word probability, for which we can answer quite reasonably. You know, what's the probability of me, I don't know, having a heart attack before the end of this lecture? Is something that's pretty gory. Let's hope that doesn't happen. I can ask any question like that. Oh, what is the probability that I will fall pregnant before the end of this lecture? And we can answer that question without having to look at frequencies of events. Now, let's consider the following setting. There's going to be a wall. This wall is of size 1 by 1. And here I have 3 walls because I'm going to do 3 examples. So think of this as the origin 0, 0. This is 1, 1. So this would be 1, 0. This is 0, 1. So it's a wall. Each side is of size 1. And I'm going to break this wall in half. And draw a bunch of, create a shaded region. Okay. So you're blindfolded. The wall is this whole thing in front of you, and you have to throw a dart. You sort of turn you around, and then you throw a dart at the wall. Okay? Or imagine that the wall sort of surrounds you like a cylinder. Now, what's the probability that dart will hit the shaded area. A half. Let's now Alright, I'll try to shout now because I've run out of sound, out of battery. Let's assume now that I put a circle. Okay, let's assume that that's a circle inside this square. I'll take your question soon. What's the probability that you will hit that circle, that you will hit the shaded area? I heard pi by 4. Okay, so the radius is a half, and it's pi times radius squared, so it's pi by 4. There was a question.
Yeah, I was going to say, how can you say that the probability is 1/2 there? How do you know if you just hit all your darts in one little tiny dot that's right in the shaded area? You get all of them in the shaded area. You never specified it like if the distribution is equal along the entire square.
Yeah, let's assume that the distribution is equal. So the setup is you're in a room. Like, think the square is the. So let's imagine that this is the setup. Let's draw it like this. You're in this room. It looks like this. But that's you blindfolded inside this room, and this room has area 1 by 1. And so you turn around and then you throw. Okay, let's assume you could throw. To make it really nice, you'd be inside a sphere. But okay, so there's equal probability of you throwing it anywhere. That's assumption. Now, let's then make this a bit more interesting. So our intuitions so far are right. So now let's consider the following case. More interesting shape. What's the probability now that you will hit the shaded area?
Area of the shaded area of the shaded region divided by total area of the square.
Okay. And how do we compute the area of the shaded region?
Integration like a curve, closed curve.
Integration. Okay, so let me take integration first. How does integration work? It's the good old, so you know, we usually break. In integration, we break the area into small regions. And then what we do is we would compute the number of red boxes that are inside the area, divided by the number of boxes. That's essentially integration. Okay, so you sum all the red boxes, you divide by the number of boxes. Now, how big or tiny can these boxes be? Okay, you want them to be as small as possible. Okay, because you need to get, you don't want to have trouble dealing with these situations. You know, the box that's neither white nor red, but it's half of each. So by making the boxes very tiny, we'll be able to deal with this problem. There's a different way of doing this.
You just throw the darts randomly, and then
That's
if you
correct.
have a uniform distribution, you'll be able to compute the area.
That's correct. The alternative is you just keep throwing darts, and then you count how many darts fell inside the area divided by the total number of darts that you threw. And that gives you a good estimate of the probability. That's called the Monte Carlo method. Okay, so, whoops, I wrote over stuff that I should have written. I'll clean the slides before I put them online. Probability, in conclusion, is a measure. It's a way of measuring chance. In this setup, that's what probability came out to be, the areas. And in the areas in this case denote the chance. What is the chance of hitting the circle? What is the chance of hitting this area? So probability is just what allows us to measure chance, or to measure certainty. How certain are we that we're going to hit the shaded area? Or equivalently, how uncertain are we in what we're doing? So a lot of things that we do in life have to deal with uncertainty. And unless we have the tools to handle uncertainty, we're incapable of being able to understand how minds work or be able to build intelligent machines. And that's why we actually pay attention to probability, because it just gives us a way of measuring certainty and being able to deal with uncertainty. Okay, so formally think of probability as a study of uncertainty or chance. Now, in probability, we talk about outcomes, and outcomes are the possible things that can happen. We say that those outcomes are events of a sample space. And mathematicians often like to use omega as the sample space, and if you have a die, your sample space has 6 possible events. The 6 faces of the die. If you have a coin, then omega is either heads or tails. So that's omega for a die. Omega for a coin would be heads or tails. Okay, so it's the possible things that could happen. We need to make a distinction between outcomes and events. The outcomes are all the possible faces of the die, but you might be interested in something other than just being able to talk about all the faces of the die. You might be, for instance, interested in the event even, which corresponds to the faces 2, 4, and 6, or the event odd, which is 1, 3, 5. Or the event greater than 4, which is a subset of the set, which is, in this case, would have 5 and 6. So we can consider all the possible events, and if you do a little bit of algebra, you'll see there's 2 to the 6 possible combinations, which you could take these. To each event, we can assign a probability. For example, the probability of even is equal to a half. The probability of greater than 4, yeah, is just 2 over 6, which is 1/3, and so on. So that's essentially just part of this lecture is about setting up the language and the notation right, so that when I talk about events, we know what we're talking about. Temperature. What is temperature?
Measure of heat.
Pardon?
It's a measure of heat.
Measure of heat. What is temperature physically? It's an average of kinetic energy. Kinetic energy of what? Molecules, particles. Now think of all of these particles, these billions of particles in this room. Those are all the elements of omega. And then you take an average of many of those guys, and that gives you a variable that you care about, and that's temperature. That's the variable that we deal with. Now, even is a variable, odd is a variable that we talk about, but they're only based on all these possible configurations of the space. Temperature is 25 degrees when that molecule over there is hitting the other molecule and this one is flying over there and so on. I however, do not want to describe what each of these billions of molecules is doing in this room. I just want to be able to tell you 25 degrees, and that's why I need to consider subsets, which are like events, and temperature being one of those subsets. I'll make this more precise a bit later, but that's sort of intuition. Now, probability, once we have defined what an event is, and we can now, and having understood that probability is just a way of measuring, we can now lay down two axioms. From these axioms, everything else follows. So this is the only stuff you would have to memorize or believe. We're going to introduce the following notation. A 0 with a bar is the null event. It has 0 probability. So like if I throw a die, what's the probability that it will be neither 0 or, sorry, neither 1, 2, 3, 4, 5, or 6? It's 0. It has to be one of those. And then we're going to talk about omega, which we've already talked about, which is everything. 1, 2, 3, 4, 5, or 6. So the probability that's going to be one of those, when I throw the die, is for sure 1, because it has to be one of those. Unless the die kind of falls in a corner, but we're not considering those out. Okay, and so, sort of thing that you've probably learned before, probabilities are measured between 0 and 1. The other thing is if you have several events happening, let's assume that this is our wall omega. Okay, so this is the whole wall that and let's break our wall into sections. Then let's call them A1, A2, A3, and A4. Then we know that the probability of omega, the probability that the dart will hit that whole space, is 1. And that's the same as the probability. In this case, omega is just equal to, I use this symbol to denote the set union, A2, A4. Which would be the same as the probability of you hitting each of these shaded areas. So this is sort of very easy to believe. It follows from our diagram before. If the whole wall, if you had to hit the whole wall for sure, then if the probability of the shaded area was 1/2, the probability of the non-shaded area was a half, and so half plus half give you 1. And the probability of the circle was pi over 4. The square minus the circle is just 1 minus pi over 4, so again the probability is sum up. So it's very basic, intuitive. The axioms are very intuitive. Now come the things that we can do with the axioms. So the first thing is that so far I assume that these events were separate. Okay, so in this picture, which we call a Venn diagram, A1 and A2, they don't intersect each other. But now we can consider a situation where two events do intersect. So in particular, imagine that you have an event A and an event B. And in this case, there's an intersection between them. Now, the problem with this is that when you throw that dart and assume that that dart ends up falling here, you're counting it twice. You're counting it as the green falling inside the green area, and you count it as falling inside the red area. So A or B is the envelope of this, and the intersection is given by A and B. And since the intersection is counted twice, we need to subtract it once. All right. Hands up who's seen this before. Good. If you haven't seen it before, you do not have the prerequisites for this class. So let's now get into the interesting stuff. Conditioning. The idea of conditioning is we want to know what happens to something given that something else has happened. Okay? So in particular, I want to know what's the probability of A supposing that I've already observed B. Very important. If I've seen B, I do not need probability to talk about B. Okay? I look at him and if you ask, if the question is what's the probability that he's male, there should be 1. I'm looking at him. All the information is being, well, not all the information is being given to me, but I'm assuming. Once something is observed, there is no uncertainty about it. Probability is only needed because we hardly observe most things. Okay, same as that problem that we had in vision that we started with for motivation. You only see a few things. The rest you have to guess, and you guess them with probability. Okay, so given that supposing you know B, what are the chances of A? And then one natural way to deal with answering this question is just count the number of times B has happened, and the number of times A and B have happened, and divide them. For example, what's the probability that it rains when it is cloudy? So you just check the number of times it's cloudy, and you check the number of times that it's cloudy and it rains, and you divide one by the other. And that gives you the probability that it will rain given that it's cloudy. So that's a simple interpretation. And instead of writing things like this, which is very long and tedious, I'm going to use this very short notation. A bar is going to mean given for the rest of this course. So when I write P of A given B, I mean that B has been observed, and an and is going to be replaced just by nothing, or sometimes a comma. So folks often use a comma, sometimes they don't use a comma. And if I multiply both sides by P of B, then I can rewrite it like this. This quantity here is called the joint distribution. The black quantity is called the marginal distribution, and the red quantity is called the conditional distribution. We also have something called the chain rule, that if you have more variables, you can keep doing the same thing. For example, the probability of A, B, C is just probability of A given B and C, and then probability of B given C, and then probability of C. So, no matter how many variables you have, you can apply this condition. Now, question for you guys. Can we write P of A and B in more than one way? Yeah. What are those two ways?
One with the marginal probability of B, in the other words, A.
Correct. So one way is P of A given B times P of B. And one way is P of B given A times P of A. Both are consistent with our definition, and there will be the beginning for something very cool called Bayes' rule that we'll talk about in the next class. Now, one more important concept. What happens when A does not depend on B? For example, I might ask, what's the probability that you will find, I don't know, the soulmate of your life, given that it's raining in Shanghai? Pardon? They're independent events, and what does that translate to in terms of the above expression? P of A and B. Correct. A is independent of B, you can drop the B, because knowing B is not going to help you answer A. So we just drop the B. And if you have 4 variables, you do the same thing. You would do the chain rule, but because one variable does not depend on the others, we just write it as a product. Independence just means that the probability of many things could just be written as individual probabilities. So it's a very nice property. We will learn later in the course a more general property of, than this, and we'll see that that's sort of the key to build a lot of AI systems to do, I don't know, car diagnosis, and it's the reason why photocopiers work so nicely these days compared to how they used to work 20 years ago. Okay, so let's now look at another example. Suppose that I have a box that is sort of like a magic box, dark box, and that there's 3 red balls inside and there's a blue ball, and you can't really, all you do is you put your hand through a hole and you pick a ball and then you check its color. Now let's assume that you do this once, you observe the color of a ball, put it aside, and then put your hand inside and take another ball and observe its color. What's the probability that the 2 balls that you observe will both be red? How would we answer that question?
1 by 2.
1 by 2.
Pardon?
Probabilities, huh?
Okay, one way is to do all the calculation in our heads and say what the number is. What would be a systematic way?
So we realize that the 2 events are independent and it's without replacement.
So we take out 1 ball and then we take out another ball. It doesn't really affect what the first ball was.
Let's see.
Then you have a choose of 3 from 4 from the first ball, and then 2 from 3 for the next one. So you see 3 and 4.
Right, those are the numbers, that's correct. Those are the calculations. But what were we fundamentally doing?
The sample space changes between the first.
You're going through all the possibilities and seeing which
Yeah.
one is
So that's
consistent
where your
with
probability changes.
Maybe I'm just remembering. You're conditioned. That's what he was doing at least. Or, in other words, this is the calculation that he did in front. Right? So right now you can do these calculations with numbers in your head. But these models will get bigger. They will have 20 or a million variables. And once they get to that scale, you're not going to be able to do these numbers in your head. But what's important is that you remember, if I'm asking a question A and B, then you use the rules of probability. A given B and then B. And here I'm assuming, I'm using this index to say the first ball and this is the second ball. So the notation here is the probability that the first ball is red and the second ball is red. So we use the comma to denote and. I could have just put a space there, but the comma is nice because it sort of looks a bit more clear in the notation. The bar always means given. And of course, if the chances of the first guy being red is 3/4, and then once the red is gone, the chances that it will be red again is just 2 out of 3. And so we have a half. Whenever you need to answer something about many variables at the same time, you apply the chain rule. That's the rule. Apply the chain rule to go from individual probabilities to a joint probability. So in order to grow, we use the chain rule. Now we'll just have to learn how to go back the other way around. Given the joint, how do we go back to individual probabilities? Once we know those two fundamental operations, we'll be able to do pretty much everything. It will have caught up with AI until the 80s. Okay, here's the shrinking operation. The shrinking operation is called marginalization. The marginalization allows you to go from A and B to just A. Okay. So, in particular, I'm using here yet more notation. By B1 to N, I mean B1, B2, all the way up to Bn. We will often in this course use this notation so that we don't have to write everything. I'm just lazy. I don't like to write long expressions at the time, so come up with short notations. And the union of all, let's assume that the union of all these sets, which are disjoint, they don't intersect, is the full sample space. Then it follows that if you sum over all of these guys, you get P of A. And this, of course, is just a sum notation. Just P of A and P1 plus P of A and P2 up to P of A and Bn. Let's look at an example. Well, let's at least first get a sort of a proof sketch. Let's assume that we have the sets B1, B2, and B3, which once you put them all together, they form the whole space. The space with the dark will definitely form with certainty. And let's now bring in another set, which I'm going to call A, the green set. Then the picture sort of says it all. The probability of A is just the probability of A intersecting with B. Sorry, like many A's and B's. Probability of A intersecting with omega. A intersect omega is just A, because omega is the whole space. But A intersect omega is just a union of A intersect B1. Let's actually do it this way. with A intersect B2, and we add A intersect B3. And the probability of the union by the second axiom is just the sum of probabilities, and intersection is just an AND operation. So this is just P of A and B1 plus P of A and B2 plus P of A and B3. Bottom line, if you have two variables and you want to get rid of one, you have to sum over all the possible values that other variable can take. Example. What is the probability that the second ball in this urn will be red? How do we answer the question?
Probability the second one was red, the first one was red, plus the probability the second one was red, the first one was not.
The intuition is correct, the details are wrong, but because you brought in the given. But you're absolutely right. So we start, it's a probability that the second one will be red, and correct, now you're 100% correct. And the first one was red, plus the probability that the second one is red, and the first one was blue. Right? Because you don't know what happened to the first ball. I just care about the second ball. And if you don't know what happened to the first ball, you can still talk about what happens to the second ball, but you need to sum over all the possible values that the first ball could take. Now this is extremely important, because typically when we have probabilistic models, we'll have thousands of variables, and you will want to make a query about just two variables. And you don't care about the other 998 variables. So to get rid of them, you just have to sum over all the possible values that those variables could take.
So this is assuming that you actually know how many balls, different types of colors there are. In real life, typically you don't know how many variables. You can't
In real life, later in the course, we will address your comment. We will deal with continuous variables soon. But to begin with, and to set up the notation and the concept, I'm just doing it keeping it simple. The notation, however, the concepts are fundamental. This is the key to the course. Conditioning, to make things bigger. Marginalization, to make things small. Less variables, more variables. Those are the two key operations. We'll be able to do this with continuous variables, with realistic situations, but the operations will always be the same. And the rules for manipulating variables will always be the same probabilistic rules. Condition and marginalization. And so we already know that this one is a half. And did anyone calculate this? I think it's 0. Oh no, it's 1 times 1/3. Oh, sorry, times 1/4. Is that correct? 1 times 1/4, which is a quarter plus a half, that's 3/4. That easy. If you just follow the rules, all these calculations are easy. If you don't follow the rules, these calculations are horrendous. If you start doing this in your head, it will take a long time. Now, following the urn, now instead of calling these things red or blue, and instead of calling these sets A or B, we typically call the sets X and enter the variable X or friendly variable X. And instead of saying red or blue or colors, let's just call them 0 or 1. Okay, because we work with computers, we like zeros and ones. And for short notation, I'm going to write it like this. If something takes two values, I use curly brackets to indicate set. It only takes two values. And I'm just saying that x is either 0 or 1. X is one of the two elements of that set. Now, as we did for the red ball, let's assume that there was a probability of 3/4 of being red, 1/4 of it being blue. We also knew that the probability of it being blue, given that the first one was red, was 1/3. Okay, because recall that the urn is red, red, and then blue. The probability that you'll get a blue, given that the first ball was a blue, is 0. Once you take the blue out, there's no more blues to take out, so the second one will have 0. It's impossible for you to get another blue ball once you've got the first one. So, question for you guys. What's the probability of 0 given 0? That x2 will be 0 given that x1 was 0?
Two over three.
2 over 3. Okay. Things are starting to get harder. You guys are taking longer now. Okay, x1 is 0, x1 is 0. When x1 is 0, two things can happen to x2. So x1 is 0. Think of x1 as 0 as you're in China. x1, 1, you're in Canada. And then given that you're in China, you flip a coin. That coin's going to be heads or tails. And when you're in Canada, that coin's also going to be heads or tails. So given that your x1 is 0, that you're in a particular coin, the sum of x2 has to be 1. So this has to be 2/3. Very important thing. Okay. What's the probability now of, let's do the other one. What's the probability that it will be 0, given that the first one was a 1? 1. For the same argument. Now, this is when you're in Canada, and if the probability of being heads is 0, then the probability of being tails has to be 1. Now, we can also write all these operations much more quickly using linear algebra. So, in particular, what I'm going to do is I'm going to create a vector. And a vector is just an array of elements. It's just a data structure for grouping elements. And I'm going to put the probability of x1 being either 0 or 1 inside the vector. And I'm going to multiply that vector by a matrix. So this is for x1. This will be x2 being 0 or 1. And this will be for x1. And the 0, 0 element will be 2/3. So 0, 0. The 0, 1 element will be 1/3. The 0 going to a 1 going to a 0 is going to be a 1. And then we're going to have a 0. Now if I multiply that vector by the matrix, I get, what's the first entry? Here. I made a mistake here, because if the first one is 1,
3/4 and 1/4.
oh, I have a mistake. mistaken with indices. Sorry guys, I apologize. Let me just quickly calibrate something here. So I have 0 going to a 1, 0 to 0, 1 to a 1. So I need 1 going to 0. So this is x2, this is x1. Apologies for that. x2 is being 0, so this should have been. I was about to break the laws of probability. That would have been bad. That doesn't happen anymore. So this should have been a 0. I got confused because I data is important. You multiply these now, it will make sense. You get a half and you get a half. And this is just the probability for x2 being 0 or 1. In other words, what I've basically done is the following multiplication and summing over x1. That's essentially marginalization and conditioning. When you do marginalization and conditioning, you're just basically doing taking a vector, which is a probability vector, multiplying by a matrix. And this is element-wise matrix multiplication. This is when you use the matrix notation. So what we're essentially doing is just manipulating matrices. In the following class, I'm going to go over base rule, which is a direct consequence of marginalization and conditioning. I will also show that this interpretation in terms of a vector and a matrix is the sort of key thing you need in order to understand how Google ranks web pages, which is what you have to, the sort of exercise you're going to practice with your own. Okay? Right, so see you guys in the
Thank you.